So we're all familiar with the bell curve, right? This special curve right here is also known as the normal distribution or the Gaussian distribution. In particular, this is known as the probability density function or the PDF of the normal distribution. No, not that kind of PDF. And the algebraic form of the PDF looks like this. F of x equals to 1 over the square root of 2 pi sigma squared times e raised to the power of negative of x minus mu quantity squared all over 2 sigma squared. That was a mouthful. In particular, mu is the mean of the distribution and sigma is the standard deviation of the distribution, where of course sigma squared is the variance. Now before we go on, I want to give a special shout out to Cantor's Monster for suggesting this as a video idea. Thank you, I appreciate it. Now today I actually want to show why the area under the bell curve will always be 1 regardless of the value of mu or sigma. So in other words, no matter what the mean or the standard deviation is for your normal distribution, the area under the bell curve will always be 1. Now to show why the area under the bell curve will always be 1, we basically have to show why this integral will always equal to 1, the integral from negative infinity to infinity of the probability density function. Now to evaluate this integral, we're going to have to use u substitution as well as something called the Gaussian integral, which I've talked about in previous videos. But to start, we're going to set u equal to x minus mu all over root 2 sigma. And then doing the usual u substitution antics, we get the following integral. Notice how the root 2 and sigma inside the integral will now perfectly cancel with the root 2 and sigma in the denominator of the fraction in front of the integral. So all we're left with now is 1 over root pi times the integral from negative infinity to infinity of e to the negative u squared du. And that integral is known as the Gaussian integral, which is well known to have a value of root pi. And so thus the root pi and 1 over root pi will cancel out, giving us 1. And so now you can kind of see why this function here has ties to probability, because as we all know, the probability of any event can never exceed 1. In fact, in general, probability density functions provide a relative likelihood that the value of your random variable will equal to some particular x value in your sample space. But in any case, I hope you're doing well. Make sure to hit that follow button for more math content. And as always, I'll catch you all in the next one. Take care.